This is the last video of Chapter 8, and it's on Section 8.6, covering natural logarithms. So a little bit of a refresher here. We have this number e here, 2.71828 repeating. Remember that from Section 8.2, when we looked at the graph of e and found out that e is the value of the horizontal asymptote of the function y equals 1 plus 1 over x to the x power. As x grew in the positive x direction, the graph was sort of going to level off at the line y is equal to 2.71828, and that value we now know today as e. And it turns out that this value of e here, we can use it as a base for exponents. So we could say e to the first, e to the second, e to the third, and e to the negative 2, and so forth. We could take e and take any power of the e as well. So it turns out, since we can use this as a base for exponents, we can have an exponential function y equals e to the x. And that function, as we see, that function, that graph, will look something like that, where we have the point 0, 1, and the point 1e, one e squared, and that point right there would be negative 1 over e, and so forth. But it turns out that this function here, y equals e to the x, has a special type of inverse, and we call that the natural logarithmic function. So here is the formal definition of a natural logarithmic function. If we have our exponential function y equals e to the x, then log base e of y is equal to x, which we more commonly express that as just ln of y equals x. So this ln here, that represents the natural log part. That's a logarithm with base e. That's what that is expressed as. So if you ever see ln of something equals something, in this case, immediately think natural logarithm. Know that that has a base of e. And it turns out that the properties of logarithms that you've learned in section 8.4 still hold true for natural logarithms as well. So here's a quick example of using logarithmic properties with regard to natural logarithms. The process doesn't change, it's still the same. You still have the power property, the quotient property, and the product property. So if we were asked to combine this natural logarithmic expression and make it a single logarithm, first you'd have to apply the power property. You get an ln of 6 cubed minus an ln of 8. And then apply the quotient property, since there's a subtraction there, to get ln of 6 cubed over 8. Well, that ln of 6 cubed over 8, that's ln of 216 over 8. And 216 over 8 is simply 27. So ln of 27 is what you would get at the end of the day when you would make that into one logarithmic expression. So here's the process to solving these natural logarithmic equations here. If we have our logarithmic equation here, ln of a is equal to y, where a is some expression including the variable x. Then here are the 3 steps. Step 1 is you have to introduce the base e to both sides to cancel the natural logarithm part. Remember, the base here is e, so to cancel ln we have to raise it to the same base. In this case, for natural logarithm, you raise it to the base e to cancel natural logarithms. That sort of leads us into step 2 by a prior property or rule of exponential functions and logarithmic functions. If you raise ln of a to the by a base of e, the e and the ln cancel, and you're just left with a is equal to e to the y. Now remember, this a is just some variable expression with an x in it that you're going to be looking to solve for. And that leads us into the 3rd step. We're looking to solve that expression, that equation a equals e to the y for the unknown variable. Remember, a could be x plus 3, a could be 2x, a could be whatever variable expression that we want it to be. Here's the first example of solving these logarithmic or natural logarithmic equations here. We have ln of 3x plus 5 equals 4. Remember, first step, we have to introduce a base e to both sides. So we get e to the ln of 3x plus 5 equals e to the 4th. The e and the ln cancel, so we get 3x plus 5 on the left side of the equation. And on the right side, e to the 4th is about 54.5982. And now it's as simple as just solving for x. 3x equals 49.5982. And divided by 3, you get x is about 16.5327. Just like that. Now the technical, more precise answer. (3x plus 5 equals e to the 4th). 3x equals e to the 4th minus 5. And x equals e to the 4th minus 5 over 3. That's the exact solution. But bear in mind, when I'm doing these, when I first did it, I was rounding to 4 decimal places, so the answer would be a little bit off if you were to go ahead and check that. But for the most part, when you would check that out, it would indeed work out. So the check would be just as follows: take this value, e to the 4th minus 5, or 16.5327, and plug it in for x here. I'm going to use this one since it'll work out just a little bit nicer for the check. Yeah. ln of 3 e to the 4th minus 5 over 3 plus 5. The 3's cancel, so you're left with an ln of e to the 4th minus 5 plus 5. The 5's cancel. You're left with an ln of e to the 4th. Well, ln and an e, they're inverses of each other, so they will cancel out. We have 4, and we have a 4 up top, so that they work. So that is a valid solution. So here's the process now for solving base e exponential equations. Process is exactly the same as solving regular exponential functions or exponential equations, but just a little twist on one of the steps. So if you have y equals e to the a power, where a is some variable expression, we're looking to solve for that variable. Now, our variable expression, a could be 3x minus 2, A could be x over 2. It could be anything, just as long as there's a variable in there that we have to solve for. First step is we have to isolate the exponential part, and what I mean by that is we have to get the exponential part here, e to the whatever power with the variable in it, and get that on one side of the equal sign. So we have e to the something equals a number or some other things. The second step is you have to take the natural logarithm of both sides. So in that case, when we take the natural logarithm, we have ln of y equals ln of e to the a. Well, if you remember, logarithms and exponentials are inverses of each other, so a natural logarithm and an exponential function with base e, they'll cancel each other out because that ln of e, that's really log base e of e to the a. A log base e with an e to the a, that'll just cancel out and just give us our a. So then when you take natural logarithm both sides, ln of y equals ln of e to the a power, you get a equals ln of y. Just remember, a is some variable expression, whatever it can be. It doesn't have to be these two expressions here. It could be an infinite number of expressions. Then the last step is to solve that a equals ln of y here for the unknown variable. So one example of solving these basic exponential equations is we have 7e to the 2x plus 2.5 equals 20. Looking to isolate the exponential part first. So to do so, we subtract the 2.5 over. Get 7e to the 2x equals 17.5. Then divide both sides by 7. You get e to the 2x is equal to 17.5 over 7. Well, if you were to divide 17.5 by 7, you get e to the 2x equals 2.5. And now let's apply, now to completely undo to get the exponential part, now all we have to do is just apply the logarithm, the natural logarithm. So we're going to take the natural logarithm of both sides, so we get ln of e to the 2x equals ln of 2.5. On the left side, we have the ln of e to something, the natural logarithm part, and the e cancel. So you get 2x on the left. Then ln of 2.5 is approximately 0.9163. And then divide both sides by 2. And you get x is about 4.4582. That's an approximate answer rounded to 4 decimal places. If you wanted to be precise, you would go from here and say 2x equals ln of 2.5. And then when you divide by x by 2, you get ln of 2.5 all over 2. And when you check that, this answer, this solution here, the precise solution, will better solve, will be nicer to use to solve or to check your answer when you plug it back into x. It'll be a lot nicer than the decimal approximation, is when you plug that value in, x equals ln of 2.5 over 2. You get 7e to the 2 ln of 2.5 all over 2 plus 2.5. Well, that's really 7e, the 2's cancel, ln of 2.5 plus 2.5. The e's and the ln's cancel, so you get 7 times 2.5 plus 2.5. Well, 7 times 2.5 will give you a 17.5 plus 2.5 will give you to 20. So I have a 20 there, and a 20 there. So this answer is right, and this answer would also be right. It would give you 20 point something something really small and close to 20, or it'll give you something like a 19.99 something that you could say is pretty darn close to 20.